Hello friend, continue to our first unit. Today we are going to cover stress strain diagram for the ductile materials, stress strain diagram for brittle material, elastic constant, that is modulus of elasticity, modulus of rigidity, and bulk modulus. Then relation between modulus of elasticity and modulus of rigidity. Again, relation between modulus of elasticity and bulk modulus. Then relation between these three moduli, that is modulus of elasticity, modulus of rigidity, and bulk modulus. After that, stress and strain in determinant and indeterminate beam, homogeneous and composite bar under loading, thermal stresses in plane and composite members. So friends, today first we are going to start our first point, that is stress strain diagram for the ductile materials. Now here all of you know what is meant by ductile materials and brittle materials. Basically materials are classified into two categories. First is ductile materials and brittle materials. So we have to calculate its strength, its different properties with the help of different tests. So after these lectures you should able to understand the silent features of stress strain diagram for ductile materials as well as for brittle materials, definitions of the elastic constant and its calculations, understand and able to derive the relations between these three modules. Here derivation is not important for you, but you should remember at least the relationship between these three modules: modulus of elasticity, modulus of rigidity, and bulk modulus. You should understand the concept of stress and strain in determinant and indeterminate beam. So what is meant by determinant beam and what is meant by indeterminate beam. Again you should able to understand the deformations in homogeneous and composite bar. You should understand the concept of thermal stress and its calculation in a plane and composite members subjected to thermal loading. So here first question is, why ductile materials and why brittle materials? So if we compare these two materials, ductile and brittle materials, both materials having the different properties. Ductile materials having the more elastic than brittle materials. If we see the examples of ductile materials, that is steel, low carbon steel, mild steel, gold, platinum, silver, copper, these are the ductile materials. And brittle materials, examples cast iron, glass, this is the examples for brittle materials. Now designer should know the different properties of materials. That one of the important properties is mechanical properties of the materials. The mechanical properties of material affect how it behaves when it is loaded. The elastic modulus of thermal materials affects how much it deflects under the load, and strength of the materials determine the stresses that it can withstand before it fails. The ductility of a material also plays a significant role in determining when a material will break as it is loaded beyond its elastic limit. Because every mechanical system is subjected to a load during operation, it is important to understand how the materials that make up those mechanical systems behave. In this stress strain diagram, we plot the relationship between stress and strain in a material for the different load and in tensile test as well as in compression test also. In this test, steadily increasing the axial force is applied to a test specimen and deflection is measured as the load increases gradually. These values can be plotted as a load deflection curve. Now, this tensile test and compression test is carried out on these universal testing machines. In this figure, this is the universal testing machine, and in short we may say it is called as UTM machines. On that machines we can conduct tensile test, compressive test, bending test. Bending test another name is flexure test. We may carry it out on this universal testing machines. So in that universal testing machines, this is the threaded screw. This one jaw is a fixed jaw and another jaw is a movable jaw. And between these two jaws, a specimen is attached. Specimen attached between these two jaws. And when the load is applied with the help of this unit, then one jaw is fixed, another jaw is in moving condition. So it applied the load on the specimen and its behaviors for different loadings we can get with the help of this software. Now, if we concentrate here, this specimen, this is a circular bar specimen is given and it is formed in proper manner. At end piece, these two end piece are fixed in the one is fixed in this upper jaw, another fixed is in lower jaw, and this is the space for that, and it is equal to near about 20D, or we may say diameter. D is the diameter for that circular bar. Now initially, when the load is applied on that side, on the specimen undergoes some deformations, and for different loading we plot this such a type of graph. So first we will concentrate on what is meant by stress strain curve. Stress strain curve is nothing but it is a graph plot between the different values for stress and strain. Stress plots on the y-axis and strain on x-axis. Initially, when the load is increased, the stress is directly proportional to strain. Hence, the stress strain graph is a straight line. So, it is shown in that figure, that is O to A. O to A, this is a straight line. This part of the graph is known as linear region. The maximum stress up to which stress is proportional to the strain is known as proportional limit. Means at the point A, that is called as proportional limit. Beyond the proportional limit, the slope of the graph starts decreasing or deviates from its original lines. Up to the point B, the specimen region, its original length when the load is removed, but from A to B, the stress is not proportional to strain. The region of the graph from O to B is known as elastic region. So stress corresponding to the point B is known as stress at elastic limit. Stress at elastic limit. It means if the load is removed from the point B, specimen regains to its original size and shape. And so original size and shape. And if we say the curve between this 0 to A, and if we say this triangle, an area of that triangle is known as strain energy stored in the body at the elastic limit, or you may say for the proportional limit. And similar way, if we increase this triangle length up to the point B, and if we take this another dotted line is given here, if we say the area under that curve, it indicates that that is the modulus of resilience. It is called as modulus of resilience. Now after the point B, the specimen is not able to regain its original length. This region is known as plastic region. Now why it is called plastic region? Because up to the point B, this specimen changes, or you may say undergo, the permanent deformations. That's why it's known as plastic region. The stress first increases up to the upper yield point. That point, C point. C point is called as upper yield point with increasing strain, and then decreases to the lower yield stress. That point, that is D point. D point is called as lower yield point. After the point D, there is increase in strain up to the point E, this distance D to E, without any increasing in stress. Only strain goes on increasing. This region of the graph is also known as yielding region. I have shown here yielding region from point C to point E. This is called yielding region. In this region, the specimen is perfectly plastic. Now next, when the yielding ends means after the point E, the stress again increases. Now see that graph from E to F. Stress increases, in additional load is required to increase in strain. Here from E to F, again load is required. This region of the graph from E to F is known as strain hardening, and maximum stress reach up to the point F. This is the maximum point. F is known as ultimate point or ultimate stress point. So the stress corresponding to point F is known as ultimate stress, or you may say that is a maximum stress. When the load is increased after reaching the ultimate stress, the cross-sectional area of specimen start decreasing in small region which is known as necking. Now, so for that we will see the previous slide. In that case, this area is called a necking, means area goes on decreasing. Now initial this area was this diameter. After that, in applying the load, this area goes on decreasing. Is it right? So that is called necking. Now after that, when the load is reached, after reaching the ultimate stress, the cross-sectional area of the specimen start decreasing in small region which is known as necking. The stress now decreases with increasing strain till the specimen ruptures or specimen fails or specimen breaks. That is called as the rupture point or breaking point. And the stress corresponding to that point G is known as breaking stress. The stress corresponding to this point is known as breaking stress. I hope you understood this diagram. In that case, you have to concentrate on that points. Terminology for that stress strain diagram: proportional limit, that is O to A is proportional limit. Elastic limit E to B, or you may say from O to B. C point indicates it is a upper yield point. D point indicates it is a lower yield point. And yielding start from the point C to E. And E to F, it is known as strain hardening. Here we have already written here in the diagram, that is strain hardening E to F. And F, that is a maximum stress or you may say it is the maximum capacity of the material to withstand the load. If we increase the load beyond this point, material undergoes permanent deformations, unnecking take place, cross-sectional area goes on decreasing, and lastly material fails at this point G. So the stress corresponding to point G is called as breaking stress. This we already discussed. Now next is stress strain diagram for the brittle materials. In that case, brittle materials we already discussed. Cast iron is one of the brittle materials, and in that case we have discussed about the cast iron specimen. Same stress procedure is same for the ductile material as well as for brittle materials. Now in that case, when we see the stress strain diagram for both the materials, you can observe that in that case here diagram is only straight line from O to A, and it slightly deflects at the point B. It slightly deflects at point B. So in that case, initially when the load is applied on the specimen from O to A, it is a straight line which represent that stress is directly proportional to strain. But beyond point A, the curve slightly deviates from the straight line, and the material fails with only a little elongations after the proportional limit is exceeded, and fracture stress at point B means at point B specimen failed. So in that case, observer or operators doesn't observe the necking formations or different stages of the neckings, but in that case in the brittle materials, material directly fails without giving the any prior permissions to the operator. Simple example, glass. Can we imagine when the glass will fail? If we applied the load on the glass, can we imagine when that glass will fail? No, it directly break. So this is the basic difference between these ductile materials and brittle materials. Now come to the points. Elastic constant, modulus of elasticity, modulus of rigidity, and bulk modulus. Now before that, we will discuss about the some points, that is modulus of resilience and modulus of toughness. Now here, this is the stress strain diagram, stress versus strain. Initially we have seen from point O to A, from point O to A is a proportional limit, and if we say here the curve and area under this curve, this gives strain energy absorbed by specimen. Now here this specimen behaves like a spring. Here specimen behaves like a spring. Now after that, if we say here another graph, for that I am taking the stress versus strain, and if we take here up to the point B, we may say this is elastic limit and if we extend this up to the point C is our upper yield point, and if we take the area under this curve, this area is nothing but it is shows modulus of resilience. This area shows modulus of resilience, and after this again here stress, this strain, we have seen this diagram A, B, C, this D, E, then it goes F and this lastly G, O to G points. So if we say the area under this curve from O to G, this area under the curve, this shows modulus of toughness. This shows modulus of toughness. Modulus of elasticity. Now next point is modulus of rigidity. It is the ratio of shear stress exerted over a body or substance to the corresponding shear strain within the elastic limit. It is called a rigidity modulus or shear modulus also. So modulus of rigidity is also known as, it is the ratio of shear stress to shear strain, and it is denoted by capital C or capital G. Now here in that tables, if we see the number of materials are given and its corresponding values of modulus of rigidity also given. For steel, that is 80 gigapascal, wrought iron 80 gigapascal, cast iron 40, copper 30 gigapascal, for the brass 30 gigapascal, and timber, that is 10 gigapascal. Third moduli is bulk modulus. Bulk modulus, it is denoted by K. The relative change in the volume of body produced by a unit compressive or tensile stresses acting uniformly over its surface. In mathematically, we may say that bulk modulus is the ratio of volumetric stress to volumetric strain. Now, why volumetric strain? Because when the load is applied on that body, lateral dimensions and linear dimensions are changes. When, if we simple examples we have seen already, circular bar. When the load is tensile load is applied on that circular bar, its length increases. It means linear strain induced in that part. But simultaneously, in the perpendicular directions, its dimension decreases. So other dimension decreases, then that is called lateral dimension decreases. It means lateral strain induced. So in that side, ultimately volume also changes. So volumetric, so that's why volumetric stress to volumetric strain. And if we say two-dimensional or two-dimensional, then sigma x, change in stress in the x direction, stress in y direction, we take the summation, then it becomes sigma. So in three-dimensional figure, we may say sigma x plus sigma y plus sigma z. So instead of that, we have written here sigma, that is the total stress, direct stress divided by volumetric stress. So yeah, again its definition becomes, it is the ratio of direct stress to volumetric strain, and it is denoted by capital K. So capital K is equal to sigma divided by EV. EV is the notation for volumetric strain, and volumetric strain is nothing but it is change in volume to original volume. Now here we have to concentrate on only relations between these three moduli, three elastic moduli. Why it is three elastic moduli? Because it behaves within the elastic limit. That's why its name is given elastic moduli. It is also called as three elastic moduli. And its fourth property is Poisson's ratio. We already discussed about the Poisson's ratio earlier. Poisson's ratio, it is the ratio of lateral strain to linear strain or lateral strain to longitudinal strain. Now relations between these three modules, modulus of elasticity, modulus of rigidity and bulk modulus, and another is Poisson's ratio also. That is the one of the property. So modulus of elasticity here, capital E is equal to twice G, or you may say here C also, in bracket 1 plus mu. Here E is modulus of elasticity, C or G indicates modulus of rigidity, and mu is called as Poisson's ratio. Second, relationship between E, J, K, and now here modulus of elasticity, capital E is equal to thrice K in bracket 1 minus twice mu. E means again here modulus of elasticity, K means bulk modulus, 1 minus 2 mu, mu means Poisson's ratio. And here we have formed one relation between these three moduli, that is from that derivations format, please check it. Now E is equal to twice G in bracket 1 plus mu, say equation number 1. Capital E is equal to thrice K in bracket 1 minus 2 mu. Now from the equation 1 plus mu is equal to E upon 2G. We have already rearranged that equations only. So mu is equal to again E upon 2G minus 1. We have to take this 1 and right hand directions, right hand side. Now mu is equal to capital E upon 2G minus 1. Is it right? So put this value in equation number 2. So E is equal to thrice K in bracket 1 minus 2 mu. Instead of that mu, we have to put this value E upon 2G minus 1. So according to that, E is equal to thrice K in bracket 1 minus 2 E upon 2G minus 1 bracket complete is equal to thrice K, solve that brackets, 1 plus 1 minus E upon G plus 2. So E is equal to thrice K, again in bracket 3 minus E upon G is equal to 3K, 3G minus E upon G. So cross multiplications, EG is equal to thrice K in bracket 3G minus E is equal to 3 into 3, 9 kg minus 3K into E minus thrice KE. So take this term minus thrice KE in left hand side, EG plus thrice KE is equal to 9 kg. So E is equal to G plus 3K is equal to 9 kg. So E is equal to 9 kg upon G plus 3K. Please concentrate on that point.